Hi everybody, and this is weak acids and bases and percent ionization today. So just to recap about weak acids and bases, we did talk about these a little bit before. So these are ones that partially ionize, so they form an equilibrium between the acid-base particles and their ions. So we've seen these before, and I'm just going to do some general formulas for us for an acid and a base, just so you can see them. But generally speaking, they're nothing that you haven't seen from the previous lesson, so you can decide how much you want to write here. So our general formula for a weak acid, if we show the water, we're going to have HA. HA just means HA for any acid, plus water, making H3O plus our hydronium ion, plus A minus. And then if we do the abbreviated form, we have HA in equilibrium with H plus and A minus. So I've just put in red the H3O plus and the H plus because when we see those ions in a solution, that tells us we have an acidic solution on our hands. Let's have a look at the general formula for the base. So B minus is representing our base here, and you'll notice that yesterday's lesson when I said we were working with strong bases, we never add water, but weak bases we do. So you'll notice I've added water here because this is weak acids and weak bases, and weak acids and weak bases we can add water to both of them, and they're going to make HB and OH minus ions. And again, I've colored OH minus ions because when we see these in solution, it's telling us we have a basic solution. So percent ionization, P, is like a percent reaction. So it tells us how many ions we have at equilibrium. So it's like a percent reaction, only the formula is easy because we can use concentration of specific ions. So if we were working on an acid reaction, what we would do is we would take the concentration of H3O plus at equilibrium divided by the initial concentration of our acid and divide and multiply by 100. Super easy. One thing that I'll remind you of is if we don't have concentration of H3O plus, that's no problem. We have a formula for that we learned yesterday, and that's 10 raised to the negative pH. We can also do the exact same thing if we have a basic solution, but there's a lot more acids in the world than bases, so you're going to find that most of the things we do are actually going to be acid centric, but I'll show you what a base looks like too. So if we were looking for a percent ionization for a base, we would have the concentration of OH on top, B minus on the bottom, which is just the original base concentration, times 100. And then again, if we wanted the OH minus concentration, if we didn't have that, if we had POH, we can take 10 raised to the negative POH to get that value. We're going to jump into a couple of different types of problems, but first we're going to just practice that percent ionization. We're just going to keep it really simple with this first example. It says the pH of a 0.10 moles per liter of methanoic acid, HCO2H solution, is 2.38. Calculate the percent ionization. So we have the concentration of the acid, it's 0.10 moles per liter. Remember, big M can be moles per liter. You've seen me go back and forth a bit. And pH is 2.38. And our job is to figure out what's the percent ionization. So there's our general formula, and we're just going to substitute in values, but we are missing a value. Right now we have the pH equal to 2.38, and we need to convert that into an H3O plus concentration. So I'll remind you that we take our 10 to the negative 2.38 here, and we should get 4.2 times 10 to the negative 3 moles per liter. Now we've got everything we need, so let's put it into our formula and solve. So we've got 4.2 times 10 to the negative 3 on top, 0.10 on the bottom, times by 100, and we get 4.2%. So 4.2% would be the ions, specifically H3O plus, at equilibrium. So a weak acid, not very many H3O pluses. So we're going to see these ionization constants once again, K's, and particularly if we're talking about an acid equation, we're going to call them Ka's, and if we're talking about a base equation, we're going to call them Kb's. So again, if we see these H3O pluses or H pluses in solution, we're going to be dealing with a Ka, and if we see OH minus, we're going to be dealing with a Kb. It's the same equation for K as it was earlier, so K is concentration of products over concentration of reactants at equilibrium, no difference there. So let's use everything we've learned so far and jump into a question. So this particular one is called a type 1 question, and the part that makes it a type 1 has been put into red here for you, and it's giving you a percent ionization. So it says to calculate the Ka for HF at equilibrium if 0.100 moles per liter solution is used and it has a percent ionization of 7.8%. Because we're still in the equilibrium unit, we're going to deal with equilibrium the way we always do. We're going to set up an ice table. So the acid they gave us was HF. So to complete the equation, we're going to add the water And then we're going to do what we practiced yesterday. We're going to move the H from the H plus from the acid to the base, and the base is going to be our water in this case. And then we're going to figure out what we make. So HF is going to lose an H and a plus, so we're going to have an F minus left over there. Put that in as liquid. And then the H2O will add an H and a plus, so it will become H3O plus, and that's aqueous. So we're setting up our ice table from here. From the problem, all we need is the I part of the ice table, just as always. So really all I needed was that first number right there. One thing that is a little bit special or different about this type of question is we're involving water, but as you'll recall from a previous lesson, water's a pure liquid, and so it doesn't have a place in a K because it's constant. So whenever we see something like a pure liquid, we're just going to put some dashes to say it's not really involved here. We don't have any ions straight away, so those are going to be zeros. And because we have zeros, we know it's going to have to shift to the right to reach equilibrium. So minus x plus x plus x. As always, I plus C makes E. And here we go. So we're looking for, in this particular case, a Ka, which makes sense because we have H3O pluses being created. So let's set up a generic Ka. So Ka is equal to our F minus times our H3O plus divided by our HF. Once again, water will not be involved here. So we can also substitute if we like here. We can say x squared and 0.100 minus x. So now we're at a place where we need to solve for x, and that's where we're going to go back to that second piece of the puzzle, that 7.8%. That's our percent ionization. So let's recall what that equation looks like. Our equation looks like this. P is equal to concentration of H3O plus divided by concentration of HA times 100%. So I've been given a P value. I have an original concentration of the acid. 100% is given. So what I'm going to be doing here is I'm going to be solving for H3O plus. And if you have a look, H3O plus is X. So that's what I'm going to use this for. So let's rearrange. So I'm going to have P times my HA all divided by 100, and that will give me my H3O plus concentration. Let's substitute and solve. So I'm getting 0.0078 there, moles per liter for my concentration of H3O plus. And again, the concentration of H3O plus is X if I look in the table. So I'm going to use this value as my X value. I'm going to go back to Ka and substitute and solve here. So my final Ka value here that I'm getting, oh, never mind, pause. Zuta Laura, I was looking at the wrong question. All right. Do over. The Ka is 6.6 times 10 to the negative 4. Hopefully that one should look familiar. All right, let's try a second type of question. Again, I've put in red what makes this a type 2. Again, it's a similar type of question, only I've given you a different piece of the puzzle. So this time I've said the pH of 0.20 moles per liter hypochlorous acid is 3.72. What is the Ka? So just a different piece of the puzzle to solve for Ka. Just like before, I'm going to set up my Ka, and my first step is to take my acid, add the water, and figure out what products I'm going to make. So my acid will deliver an H plus in this direction. I will leave an OCl minus behind and make H3O plus ions. And then I'm setting up my ice table. They've given me 0.20 moles per liter of my first ingredient. Water, remember, I exclude. I don't have any ions originally, so I'm going to shift to the right, and I plus C makes E. All right, let's set up our K. So Ka, again, because I'm dealing with H3O pluses, I've got OCl minus H3O plus, and it's divided by HOCl, again, excluding my water. Again, I can substitute in, so I'm going to put it in gray here. So I've got x squared 0.200 minus x. So if I can solve for x, I can solve this problem. So going back to the problem, let's have a look at what they gave me this time. This time they gave me pH equal to 3.72. So that's convenient because I know that H3O plus is equal to 10 to the negative pH and H3O plus is X. Hooray! So let's put that together. So X, which is H3O plus, is going to be 10 to the negative 3.72. And I should get a value here of 1.9 times 10 to the negative 4, if I'm not mistaken. Let's go back to our original equation, substitute and solve. So I've substituted back in, and I am getting 1.8 times 10 to the negative 7. We're going to add a part B onto this, and what I want to do is I want to go back to that equation we first learned, which is my percent ionization, and just see how it works into a question like this. So let's set it up. So here's our equation. Remember, it's pretty simple. We've got our concentration of H3O plus, which we recently found, divided by concentration of HA, which we found in the I part of the ice table. It's part of our word problem, times 100%. So straightforward, we're just substituting in values. So we've got our H3O plus concentration. We found it to be 1.9 times 10 to the negative 4. And then they gave us the original concentration of acid as 0.2. We're going to divide and then multiply by 100%. And we're getting a very small value of 0.095% here. So very few ions at the product stage. So time to try on some homework. We've got a few questions, only 6 of them to try on for size today. Pretty straightforward. Again, I'll put in my Google Doc for any homework requests, and so long as I have them by 8:30 tomorrow, I will make you a little video taking those up for you. Cheers!